talk is Qaasim Shafi, Imperial, and he's going to tell you all going to be recorded, right?
Yeah, that's
yeah.
Right.
And he's going to tell us about Quasimaps and accordions.
Hey everyone, so thanks for letting me speak. So yeah, so the title is Quasimaps and accordions, and so no musical instruments, but it's about curve counting theories, and Quasimaps is kind of a less famous curve counting theory. So I'm going to start with a slogan that may or may not help some people, and then I'll go from there. So okay, so the slogan is Quasimap theory is like Gromov-Witten theory with base points. But if you don't know what Gromov-Witten theory is, then this isn't very helpful. So maybe I'll zoom out a bit and this will become clear later. So I'm just going to tell you what like how modern curve counting theories work first. So curve counting. So what you start off with is you start off with some smooth projective variety x. So maybe I draw. So here's my x. So this is my variety. And then what I do is I associate to it a moduli space. So right, m of x, which is something like curves in x. So the points of this moduli space are like curves inside my variety. So curves in x. So here's a curve in x. So okay, so I take my variety and I associate to it some moduli space, whose points are curves, and then from there I do some integrals over this moduli space, and these are called invariants, and you should think of them as like curve counts. So roughly I'm thinking of counting certain curves inside the variety x that satisfy some conditions, but interpret this loosely because it's not always literally true. And to go from the second step to the third step, I need like, there are kind of two important things I like always need. So to go from here to here, I always need m of x to be proper or compact. And I need it to be smooth, or something that's called virtually smooth. But maybe I'll probably ignore the second one. Okay, so I'll start off with an example. So they're kind of, or one of the more famous. So one of the kind of more famous curve counting theories is Gromov-Witten theory. And I'm just going to set x to be P2 for now. Okay, so let x be the projective plane, and then I have to tell you some moduli space. So I'm supposed to tell you what m of P2 is. Okay, well, I actually also have to tell you some extra numbers. So we don't just consider curves in P2, but curves of some type. So okay, so I have to tell you a number. So this number 0 is going to be the genus of the curve. This number is going to be, I label some points. So this is some markings. And then I also tell you the degree. So the degree, this is going to be 2. So this is just an example. So this is the degree. So yeah, so what's this? So this is the space of, okay, so genus 0, degree 2 curves with 2 markings inside P2. And in Gromov-Witten theory, you don't consider embedded curves, you consider them with a parameterization. So there's like a morphism from the curve to P2. So these are, okay, so these are parameterized. These are parameterized curves, C to P2 of, with 2 markings. So that's 2 points in C, of genus 0, degree 2. And the other condition is that it has to be stable. So it doesn't really matter what this means, but there's some condition on it. I'll basically ignore it. And okay, so maybe I'll just start off with some examples. So an example is consider the curve in P2 where the domain is P1, and I have my map is given in homogeneous coordinates by Z0, Z1 goes to Z0 squared, Z0, Z1, Z1 squared. So this is a perfectly good degree 2 map from P1 to P2. And as soon as I pick 2 points on the P1, this lives inside this moduli space. You know, in fact, I could, you know, for any, if I give you any non-zero complex number, you know, I could give you the map so I fix some t, some non-zero complex number, and this also defines the curve in my moduli space. Okay, so I've just given you, so every complex number I've given you some element of this moduli space, so some curve in P2 of degree 2. So the question, the first question I'm just going to ask is what happens as t goes to 0? So yeah. So what happens? Okay, so if I just like naively set t equals 0, so we get this okay, so if I just set t equal to 0, this is what I get. I have these kind of 3 sections, but now that I've no longer got a morphism because this is not defined. I guess 1, 0. So not defined. Got 1, 0. So but there's some limit. This is some proper moduli space. So there's a limit. So maybe I'll just say what it was, say what it is. So I'll just draw a quick picture. So for t not equal to 0, so this is my P1, and I guess there's supposed to be two markings on there, and this is supposed to be a picture of P2. And okay, so for t not equal to 0, it's just a degree 2 map. And then okay, so there's some limit, and I'll tell you what it is now. So okay, so there's my P1. Here's 2 markings. What happens is this at t equals 0? Well, I was a bit sloppy when I gave you this definition, because really I should have just said the word nodal as well. Sorry, I realize I haven't moved the screen. So what happens is I get another component attached here, and then the morphism is degree 1 on both. So this is the limit in the moduli space of stable maps, which works perfectly well. To see where this came from, you could consider the rational map from P2 cross A1 to P2, and then blow up at the base point, and that's where the extra component comes from. But it's not really important. So this works fine. But the point I'd like to make is that there was like another. We kind of stumbled on another solution already. If we'd kind of allowed our morphism to acquire base points, we could have just let the limit be the thing at the top here. So if we allowed our morphism to acquire base points, we could have had as the limit this kind of not quite morphism. So I've technically given you more. It's more data than a rational map because I've told you 3 sections. But if I'd given you this limit, this would have been a perfectly good limit. And indeed, this is an example of a quasi-map. So this is a so long as I have the 2 markings floating around, this is a so.
You're not cancelling the Z1. You're not telling us that you.
That's right. That's right. I'm telling you the data of these 3 sections. So I'm not cancelling the day 1. Indeed, if I looked at it as a morphism, it would look like a degree 1 map to P2 with a kind of weird base point. But I'm keeping the data. So this is degree 2, and I'm telling you, if I just gave you the rational map, I wouldn't be able to know how many powers of Z I pulled out or something. So I'm keeping that data. So in fact, this is so this one is a stable, but that word's not, I'm not really going to talk about this word, stable quasi-map to P2. Okay, so now maybe I'll give a definition.
But Qaasim,
Mm-hmm.
you should also say, I mean, you are collapsing some information because you had that other component, and it could have been any line.
That's right. That's right.
And you're totally forgetting about
That's
what
right.
that was.
That's right. That's right. That's right. And this will exhibit itself in the fact that the Quasimaps spaces are kind of more simple because there's less moduli than the Gromov-Witten spaces.
Which is one
One
of the
release
reasons.
station only birational.
Mhm.
Which is one of the reasons why you do it.
Point you're sweeping out the traffic. You're not saying it's right and goes to infinity.
No, I'm not.
Deal with that later.
Mhm. So okay, so yeah, so I'm going to give you a definition. That's okay. So so definition. So okay, so remember I had to tell you a genus, a degree, and a number of markings. So a genus G, N marked, degree D, Quasimap to, okay, let's just do Pn, is, okay, well, I've got to tell you a curve. So so a nodal genus G curve. A line bundle L on C of degree D. And then I have to tell you some sections. So U0 to, so this before it was 2, but this time it's, well, 3 sections. This time there's n plus 1. So some global sections such that so I'm gonna allow some base points, but like not too many. So there are kind of finitely many base points. Away from nodes and markings, so they're not allowed to hit the kind of nodes or the marking. Okay, so that's this is okay. Okay, some nodes. So this is a Quasimap, and then if I'd done this properly, I would have told you what a stable Quasimap is, but it's okay. But if I did stable Quasimaps, form a proper moduli space Q and D, which is yeah. And so using this, you can define some, and it's virtually smooth, and you can define some invariants or something. Okay, so there is unlike Gromov-Witten theory, you can't do Quasimaps for any variety. You have to have, so we kind of use the fact that the functor of points of projective space had this kind of nice line bundle section description. So you need something similar. So just a quick remark is that Quasimap theory exists for any, say, reasonable GIT quotient.
You're finitely many base points away from those markings.
That's right.
So does it mean you are allowing some of them to be on those markings?
No, sorry, no base point can be on any marking or any node. Sorry, it might be badly written.
No, yeah.
But
You're doing some kind of validative criteria to prove that it's proper.
that's right.
And so you have to be able to tell me at the end of the lecture what you do when t goes to infinity.
Okay, perhaps at the end, because yeah. Okay, so okay, so let's say but maybe the question is like why? Why does, like, we already had Gromov-Witten theory, man? Like why just add more curve counting theories? Just so the reason is there are these wall crossing formulas. It's known as wall crossing formulas, relating Quasimap to Witten invariants. And moreover, the Quasimap spaces are typically simpler for the reason that Alessio pointed out earlier. I don't know if I guess the camera didn't hear, but in the previous example, we had our limit had two rational components, but in the moduli space of stable maps, I get to choose where that line is. So I get a choice of line in P2 through a point, whereas in the Quasimap world, I just have a base point. There's no moduli there. So the Quasimap spaces are simpler, and so one way of sometimes calculating Gromov-Witten theory is to do the Quasimap calculation and then do these wall crossing formulas. So Quasimaps spaces are simpler, so can be used to compute Warwick invariants. Okay.
I mean, it's basically, if you look at P1 to P2, like you have there, it's just a bunch of polynomials of P1.
That's
It's
right.
a projective space, that's what it is. It's a projective space of polynomials.
Yeah, yeah. For example, if you did like genus 0, 2 marked Quasimaps to P2, the space of degree 1, the space is P2 cross P2. And the Gromov-Witten space is the blow up of P2 cross P2, something like the diagonal or something. But okay, so that.
You could say it's simpler, but you know, the difficulties of Gromov-Witten include, for example, wrapping, where in multiple covering.
Mhm.
And so the map, you know, the geometric map doesn't tell you.
That's right. They still may not give you genuine curve counts, even if
Yeah,
the spaces are, or say blowdowns or something like that. But they might be easier to do integrals on.
Yeah,
But yeah, that's absolutely right. You still have multiple colors and all of this thing. Okay, so that's like part 1. So, oops, shit. So part 2 is about relative curve counting theories. So we're gonna. Oops. Okay. So now we're going to talk about relative curve counting. Okay, so last time we started off with a smooth projective variety X. So instead, start with a pair XD is a divisor. For us, it will be smooth, but sometimes it's simple normal crossings. And okay, so so you start off with, so okay, let's draw another picture. So here's X, so this is X, and inside here's my divisor. And then, okay, all I have to do is I have to associate some moduli space. So relative Gromov-Witten theory is going to be about counting curves in X, but with certain tangencies to the divisor D, so fixed tangencies. So okay, so then I have to tell you some moduli space. So there's a moduli space here, and this is something like, so here's X again. So this is D, here's X, and then I have to tell you some curves, but the curve is now going to have some fixed tangency to D. And then you do the same thing again, as long as you have these two conditions, you go and calculate your invariance. So that's how relative curve counting theories work. So, okay, so how about we do, so let's say, okay, no, we'll start with, okay, so as before, we'll do the Gromov-Witten case. So let's do relative Gromov-Witten theory. This time let's fix, so let's say X is P2 again, and D is going to be a line given by the first coordinate vanishing. Okay, so as before, I have to fix some numbers. So okay, so G is 0. I have to tell you some markings, and this time N is going to be 1. And I'm also going to, okay, so let's just set the degree to be 2. So, yeah, the time I'll drop that. Okay, so okay, so we're doing P2 relative align. But before we do that, I'm just going to write out the kind of ordinary Gromov-Witten space again. So, okay, so if I have, so this is times our 1, so genus 0, 1 marked. So the curves are in P2 and the degree is 2. So, okay, so, okay, so yeah, no, I'm not going to write what it is. So yeah, so these are parameterized curves to P2 from a genus 0 nodal curve of degree 2. So it's kind of what we had before, but I dropped a marking. And inside here, I can look at curves, sort of C, which hit the divisor L with, let's say, tangency 2 at this marking P. Okay, so I've got all conics, all parameterized conics in P2, or parameterized degree 2 maps from a rational nodal curve to P2, and I'm going to pick out the ones that have tangency order 2 at this special marking that I've chosen.
Where is P?
So P is just a point on the curve. This number on C. That's right. Sorry, I'll write that. Yeah, that's right. P is a point on the curve. It's the marking corresponding to this one. Yeah, thanks. Okay, so I'm going to pick this out. But we have the usual problem. This is not proper. I mean, I've just told you it's that, but this is, yeah. Okay, so why? So example, so consider the limit as t goes to 0 of, so let's say P1 to P2 and t, yeah, of, so the map is going to be Z0, Z1 goes to, so let's say t, Z0 squared, Z1 squared. So I've changed it slightly, Z0 squared. So, okay, so I've given you another bunch of points in the moduli space, and for t, and okay, let's say, okay, and so in this case, I've set p to be 0, 1. And so for t not equal to 0, these live in my my set here. These are conics which hit the line given by the first coordinate vanishing with tangency order 2. But when I set, but that's fine. But for when t equals 0, okay, this time we don't have to worry about base points. We do get a genuine morphism, but it kind of fell inside the line. So yes, this is also sad. So P1 mapped entirely into L. So at which point I can't really say what the contact order is, but I guess it's infinite. So okay, so this space wasn't proper, so I need. Yeah, I guess so. But I fixed the contact order to be 2. I only care about, and this would also. That's right. That's right. Not at least 2 or something like that. That's right. I tell you, part of the data of relative Gromov-Witten theory is the contact order at each marking. So instead of just telling you the genus, the degree, the number of markings, I also have to tell you like a tuple of numbers for each alpha 1 to alpha n, where they specify the contact order at each marking. Sorry, in this case, there's just one marking, so I just have to tell you the tangency. And I'm just insisting, I could have said there are 2 markings and they both hit with tangency order 1 and 1 at each, for instance, but we'll go with this example. Did I just write on that board? Yeah, I did. Okay. 28. Okay. Okay. So what's the solution this time? Yeah, rub. Okay. So there are 3. So this time we get some choices. So there are 3 solutions. But I'm going to mention all 3. Well, I'll write them, but we'll only care about the second one really. So the first one is to just take the closure inside the absolute space, which can be done. So inside, I guess in general, would be mg and x beta. But this works. This does work, and this is due to Gatman. And this works in genus 0, mostly because of the virtual business. Like only in genus 0 because of the virtual business, and when D is smooth and very ample. And very ample. Okay, so this, the second solution is, so now we get the second word of the title, is to use accordions, or sometimes they're called expansions. But if I called my talk expansions, I wouldn't get a musical instrument in the title. So use accordion, so this is due to Jun Lee, and this works for, so any genus for D smooth. And the third solution is to use log structures. Yeah, whatever. Structures, which is Abramovich, Chen, Gross, Sieber, and works for any genus and D simple normal crossings. But I mean, since then you can use the second one to do the two simple normal crossings case as well. But in any case, we're just going to be talking about a smooth divisor, and we're going to mostly we're just going to focus on this one. Okay, so I'm going to go to the other side, 31. Are there any questions? No? Okay. Okay, so what was I? So, okay, so two, so this was solution 2. So this is the accordions business. So I'll just, yeah, I'll draw again. So we have, I guess it's just X, and we have some divisor D, and then we have, is there another color? It's okay if it's not. Thought I saw one. Okay. Underneath. Thank you. Thank you. Okay. And so, okay, so we had some, so if it's, we had two cases. We had like T not equal to 0, and we had, okay, maybe I'll just break the curve up. So we had, this is my mark point, and then let's just say there's another component here. And then when T equals 0, we had, so this is D and this is X. And then we had, okay, this component didn't change, but maybe this one kind of fell inside. Okay, so we have to solve this. And the solution is to instead modify the target. So the kind of point is that it didn't have enough room to tell us that it was contact order 2. It kind of ran out of space. So solution, modify target. And so what do? You replace X in this divisor. So you kind of stick on this P1 bundle over D. So this is a P1 bundle, such that there's a copy of D here as well. So this is D and this is D. So the infinity D and the 0 D. And then what you can have is you allow yourself space to have, so I guess you still have the same component here, but now you've given yourself enough space so that you can have, you'll have things that hit this thing with the right contact order at the kind of infinity end of D instead. So you just provide yourself with enough room. So I don't want to say too much, but I'll just say, okay, so where does the name accordion come from? So accordion, the point is that you need to, sometimes you need to go more than one level. So you end up with pictures that, okay, so I have my D here, but then I stick on one level here, and then I have to stick on another level here, and then I have to go again. And this is supposed to be my accordion. So I have like P1 bundles glued to each other along copies of the divisor D. So each of these kind of lines are supposed to be the divisor D. And when I say contact order, I mean contact order with the right, the right contact order with the last D. Sorry, that may have been a bit vague, but it's okay. So,
Was sort of magically changed the curve. I had this curve which was a parabola touching D,
uh-huh.
and it's sort of now stretching through the whole of that accordion, right to the very last.
Yeah, I mean, with if you have a,
To the end.
that's right, that's exactly right. If
So
you,
how is that flat family?
sorry,
How can that be a flat family of maps?
yeah, I don't.
No, I mean, you drew the original, right?
This one?
At the very top.
Yeah,
Okay, and then the curve is sort of flattening down to.
to here.
Yeah.
And I need something to fill in, but not this. I don't want this because I can't tell you what the contact order is. And I'm telling you that the missing thing looks something like this.
But I think it still works that if you accept that you can modify the target that way, you know, so maybe you take P2 times the disk and you blow up some lines inside the central fiber. Then you're still taking the flat closure of that family of curves, and it will end up with that. Right.
I can't see that in the calculation.
Okay. So the last thing I just want to say is the Quasimap theory. Okay, so the last thing is relative Quasimap. So, so I think the motivation for kind of thinking about,
This is what you do, right?
yeah, that's right, that's right. There we go. We finally got there. That there are these kind of wall crossings which give you ordinary Gromov-Witten invariance. Perhaps there are wall crossings which will give you relative Gromov-Witten invariance, or at least this is what Navid tells me. Navid. Okay. Sorry. Yeah. Thank you. Okay. So yeah. Speaking of Navid, so Battistella and Nabiju used, so I guess in this it was technique one. So they're taking the closure technique to give relative Quasimap theory. In this case, so for exotoric variety, D smooth, very ample, but in genus 0. So what I'd like to do is use something like this to kind of get rid of some of the restrictions. So want 2, and technically a bit of 3, but I won't talk about that. To get rid of some restrictions. Okay, but before that, I just want to remind you what I was compactifying. So before that, want to remind you what we're compactifying. So okay, so we'll do P2 in a line again. So what was a Quasimap to P2 in a line? Well, I told you a curve, I told you a line bundle, and then I told you 3 sections, and then maybe there's some markings. So okay, I'll put some markings. Okay, so this is, let this be a quasi-map to P2. So yeah, what even is tangency? So if I had a morphism from my curve to P2, then tangency at P to the line L means the order of vanishing at P of the pullback of the section which cut out the divisor. But we don't have a morphism, but we do have kind of the pullback of the section still. So so tangency for a quasi-map is the order of vanishing at P of just U0, which is kind of F star X0 if there was a map. So in the case where there are no base points, these are really the same thing, but because there's no base points, I can't literally pull back the equation that cuts out the divisor. So the analog to, did I just rub it out? To the kind of subset of the absolute stable map space where they had like conics which had contact to order 2 is the kind of quasi-maps where the first section vanishes to order 2 at the right marking. That was a lot of words. Was that okay? Maybe not. Okay, there's some tangency for quasi-maps. And but the problem is, so okay, problem can't do quasi-maps to, we can't do quasi-maps to this kind of weird expansion because it's not like a reasonable GIT quotient. I said you can't do, you can always define a morphism to it, but it doesn't have the right structure. So instead, we're just going to expand the kind of bit of the quasi-map we need. So okay, so we have a line bundle section pair which in the above case was LU0. And you know, this is okay. This is the same thing as a map from C to this weird quotient stack. Okay, this may seem weird, but you know, a function on a curve is the same thing. A regular function on a curve is the same thing as a map from C to A1. So a line bundle section pair is the same thing as a map to A1 mod C star. I mean, you can take this as a definition, but in any case, now I have an actual morphism.
The definition of A1 mod G.
Yeah, that's right. As the moduli space of line bundle section pairs.
And square brackets means that it's the stack.
That's right. That's right. So the only reason I've gone through this weird stack is that now I have a genuine morphism, and so an analogous construction to this expansion business exists for A1 mod GM. And so instead I expand this and ask the order of vanishing of the section to be the right contact order at the last level. So instead, expand A1 mod GM and insist on getting the correct order of vanishing the last level. Okay, and then final thing, if you do this, well, I mean, if I've done it right, proposition, okay, I wouldn't say what it is, but this gives a proper moduli space. So yeah, I'm conscious of time. I know they said there's only 2 talks, but I think this is kind of reasonable. So so yeah, maybe I'll stop there. And oh no,
Well, explain this thing a little bit. You explained to me the other day.
that's right. Okay, I will say.
People are.
Okay, I'm.
We do maths.
Okay, okay. So sorry everyone. Unless you use a request, you'll have. I'll do another minute. Okay, so okay, so I'll just say okay. So okay, so okay, so okay, so I didn't really tell you anything about this A1 mod GM or expansion of it. So maybe I'll just give you a quick idea of what it looks like. So expanding A1 mod GM. So okay, so what's A1 mod GM? Okay, well it's the complex line modded out by C star. So I have like 2 orbits. I have the non-zero points and I have the 0 point. Okay, so there's 2 points. There's like an open point, and then there's like a, so okay, so this is okay, so this technically has stabilizers, and this is like a point. So there's 2 points. That's what A1 mod GM is to me. Okay, and if I expand A1, so this is A1, and here's 0. So just say to first level, what I do is I attach P1 to the 0 point. So I have, so my 2 divisors are kind of here, 0, and infinity. So this is an expansion of A1. Okay, so what's an expansion of A1 mod GM? Okay, well, I have my kind of open point here, and I have my BGM, which is my divisor, my 0 point. And what I do is instead of gluing P1, I glue P1 mod GM. So okay, so P1 mod GM is okay. I have an extra point, so I have so when the one of the coordinates is 0, I get a stabilizer point. When the other coordinate is 0, I get a stabilizer point, and the rest of them get identified in the orbit. So I have okay, so I have a BGM here, and I have some open point here, and then I have another like infinity BGM point, which means like a stacky point with stabilizers. And then the contact order condition is moved from here to here. Okay, yeah, I think that's possibly enough. But I'll just say.
But tell us what is a map to this expanded thing?
Yeah. So okay.
Yeah,
So yeah. So a morphism from yeah. So a morphism to A1 mod.
So we're talking about compactifying a family with given parameters of maps to there. And what we're taking sort of the first non-zero or the first non-trivial Taylor expansion in the parameters and using that as the actual map.
That's right. So I keep the data of the Quasimap, but the problem really was just, I isolated the problem by just talking about the line bundle section pair. So the data of this relative Quasimap is the ordinary Quasimap, but now I just add the enough data to tell me that I get the right contact order, which is why I expand this. No, I think I'll stop there. We can ask questions if you want, but thanks for listening.